What if black holes aren't just the ultimate cosmic destroyers, but gateways? Gateways to realms beyond comprehension. Realms not of this universe. Portals not of space, but of possibility. The idea sounds like science fiction. A thrilling, terrifying hypothesis that has haunted physicists, cosmologists, and science fiction writers for decades. But here's the chilling part. It's not entirely fiction. Not anymore. Somewhere between Einstein's equations and the eerie silence of deep space, a theory was born. A theory that suggests black holes might not be the end of the story, but the beginning of something far stranger. To understand where this idea comes from, we need to journey back to the early 20th century. Back to a time when our understanding of the universe was, quite literally, expanding. In 1915, Albert Einstein unveiled his general theory of relativity, a radical new view of gravity. Gravity, he proposed, was not a force pulling objects toward one another, as Isaac Newton had suggested centuries earlier. Instead, it was a warping of the very fabric of space and time. Massive objects like stars and planets bent the space-time around them, and smaller objects moved along those curves. This framework didn't just change how we understand motion, it changed how we understand the universe itself. And it gave birth to something even stranger, the prediction of black holes. Einstein himself was skeptical of black holes. He didn't believe nature would allow such bizarre objects to exist. But just months after publishing his equations, German physicist Karl Schwarzschild found a solution that implied something remarkable. If enough mass were compressed into a small enough space, it would warp space-time so severely that nothing, not even light, could escape its gravitational pull. A singularity. A point of infinite density. At first, this was seen as a mathematical curiosity, a weird edge case of relativity. But as time went on, the evidence began to pile up. In 1964, physicist Roger Penrose showed that under general conditions, the formation of singularities was not just possible, it was inevitable. Soon after, astrophysicists began detecting strange cosmic X-ray sources, rapidly spinning objects, and stars orbiting invisible companions. The black hole moved from theory to observation. But here's where things take a turn. As physicists dug deeper into black hole theory, they discovered something troubling. General relativity predicts that at the core of a black hole lies a singularity, an infinitely dense point where the laws of physics break down. But infinity isn't just a big number, it's a sign of failure. A sign that the theory can't fully explain what's going on. And when a theory breaks, it often means there's something more, something hidden just out of reach. This theoretical collapse gave rise to a question. What if black holes aren't dead ends? What if they're doorways? In the 1930s, two brilliant minds, Albert Einstein and his collaborator Nathan Rosen, attempted to peer into this unknown. They revisited Einstein's equations and found something extraordinary. Just as space could curve around a star to create gravity, under the right conditions, space-time could fold in on itself to form a bridge, a tunnel, a connection between two separate points in space-time. This became known as the Einstein-Rosen bridge. At first glance, it seemed purely theoretical, a mathematical anomaly. But the more physicists looked into it, the more serious the idea became. If black holes could connect to other regions of space-time, or even other universes, they might not be singularities at all. They might be portals. To explore this idea, scientists began building mathematical models. In the 1950s, physicist John Wheeler coined the term wormhole, a shortcut through space-time, like a tunnel through an apple. If space-time were the apple, the wormhole would be the path the worm takes to travel from one side to the other without crossing the surface. In theory, wormholes could allow for faster-than-light travel, time loops, and connections across vast cosmic distances. And yet, there was a catch. Wormholes, as predicted by general relativity, are unstable. They collapse the instant anything tries to travel through them. But physicists weren't ready to give up. The idea was too compelling. In the 1980s, they theorized that exotic matter, material with negative energy density, might stabilize a wormhole. Such matter has never been conclusively observed, but the mathematics checks out. In fact, recent studies on quantum fluctuations hint that such exotic conditions could, in theory, exist. If a black hole could be connected to a white hole, the theoretical opposite of a black hole that expels matter, it might create a traversable wormhole. A one-way or even two-way portal through space and time. But what would that mean for our universe? Suddenly, black holes were no longer just cosmic vacuum cleaners. They became candidates for something far more bizarre. Something that made even the most grounded physicists pause. Stephen Hawking, One of the foremost thinkers in theoretical physics proposed in the 1970s that black holes aren't completely black. Instead, they emit a faint radiation, now known as Hawking radiation, and slowly evaporate over time. But this raised a new paradox. If black holes disappear, what happens to the information they contained? Quantum mechanics insists that information cannot be destroyed. Yet black holes seem to do just that. This led to the black hole information paradox, a conflict between quantum theory and general relativity. It remains unresolved. But one potential solution? That the information escapes not into nothingness, but through a wormhole, into another universe. Now imagine this. A star collapses under its own weight. A black hole forms. But instead of becoming a singularity, it funnels its contents into another realm. Not just across space, but across dimensions. Our universe may be just one side of a larger, unseen structure. This brings us to one of the most haunting implications of the portal theory. If black holes are gateways, then where do they lead? Are they passages to distant parts of our own universe or tunnels into entirely separate realities? Could they be the key to understanding the multiverse? For decades, this idea sat at the edge of science, dismissed by some, championed by others. But today, the line between science fiction and science fact is blurrier than ever. With tools like the Event Horizon Telescope capturing the first image of a black hole shadow in 2019, and quantum gravity researchers uncovering strange overlaps between wormhole math and quantum entanglement, the theory has regained momentum. Still, skepticism remains. Most physicists agree that we lack the technology and perhaps the courage to test these ideas directly. Sending a probe into a black hole isn't just difficult. It's impossible with current materials. The gravitational forces would tear any object apart. And even if it survived, we wouldn't receive a signal back. Nothing escapes. But theories don't die because we can't test them yet. They persist because they explain. And this theory, wild as it sounds, explains quite a bit. It explains why black holes might not erase information. Why the mathematics of general relativity permits bridges. Why the universe appears so finely tuned for complexity. Perhaps because it's not alone. Perhaps because it's connected to something else. The terrifying part? If black holes are portals, they might not be empty. They might be highways, corridors, channels of transfer. And if something can travel through them, could it already have? It began, as most scientific upheavals do, with an anomaly. In the late 20th century, astronomers studying the supermassive black hole at the center of our galaxy, Sagittarius A*, noticed something strange. Stars were moving in bizarre orbits, not unlike moths circling a flame. That in itself wasn't unexpected. After all, black holes exert incredible gravitational pull. But their patterns were too clean, too synchronized, too perfect. In 2002, a star now known as S2 passed dangerously close to Sagittarius A*, moving at more than 5,000 kilometers per second. What startled researchers wasn't just the speed, it was the survival. By all classical expectations, the star should have been torn apart by tidal forces. But it wasn't. It slingshot around the black hole and continued on its orbit, relatively undisturbed. Scientists initially chalked it up to luck or orbital eccentricity. But then it happened again. And again. A pattern emerged, one that hinted at something more. Something shielding these stars from annihilation. Or perhaps redirecting energy in a way we didn't yet understand. Then came GRB 070125. On January 25, 2007, a gamma-ray burst was detected in a relatively empty region of the sky. Gamma-ray bursts, GRBs, are among the most energetic explosions in the universe, typically linked to the collapse of massive stars into black holes. But this one defied classification. Its duration, energy spectrum, and afterglow didn't match known profiles. More puzzling, the region it originated from showed no signs of star formation, no supernova, no stellar nursery, no evidence of recent cosmic violence. This event reignited speculation. Could some black holes be ejecting matter in ways we don't understand? Could they, in fact, be ejecting it somewhere else? As observation technology improved, physicists began to notice other oddities. Take black hole jets, for instance, those twin beams of high-energy particles that shoot out from the poles of some spinning black holes. According to relativity, nothing can escape a black hole past its event horizon. And yet, jets can extend hundreds of thousands of light years into space. The particles aren't technically coming from inside the black hole. They're thought to originate from the swirling accretion disk just outside the event horizon. But the sheer energy, coherence, and directionality of these jets raise questions. Why so focused? Why so persistent? One hypothesis? The magnetic fields generated by the spinning black hole twist spacetime so violently that they launch particles through a process called the Blandford-Znajec mechanism. But that's just a name. The truth is, no one really knows how jets remain so stable for so long. And some physicists argue these jets may be more than emissions, they may be information channels. Or worse, test patterns for traversal. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. Two black holes had collided, sending ripples through space-time itself. But hidden within the noise of that first detection were subtle asymmetries, tiny irregularities that didn't fit cleanly into standard models. These blips have since been observed in other detections. While most physicists attribute them to measurement error or noise, a few researchers have proposed alternative explanations. What if these asymmetries are signs of energy bleeding into or out of other dimensions? The idea might sound absurd, but it gains traction when seen in the context of string theory and brain cosmology. In these frameworks, our universe is a three-dimensional brain floating in a higher-dimensional space. Matter and energy are typically confined to our brain, but gravity is not. This could explain why gravity is so weak compared to other fundamental forces it might be leaking into other dimensions. And if gravity can leak, maybe something else can too. Back in the observable universe, astronomers noticed a peculiar alignment of quasar light in opposite directions of the sky. These quasars, ultra-bright galactic cores powered by black holes, should have random orientations. But in 2013, researchers from the University of Liège found that over a span of billions of light-years, dozens of quasars exhibited parallel polarization. It was as if some vast hidden structure were coordinating them. The press dubbed it the axis of evil, though the term had already been used to describe temperature anomalies in the cosmic microwave background. Regardless of nomenclature, the implication was chilling. Something beyond our universe might be tugging at the cosmic fabric. And black holes could be the tendrils connecting us. These unexplainable patterns, star behavior, particle jets, gravitational echoes, aligned quasars, form a web of evidence. On their own, they are anomalies. Together, they whisper of a deeper order. Still, the portal theory needed something more. Something concrete. Something terrifying. That came in 2019 with the Event Horizon Telescope's image of M87*, a supermassive black hole in the Virgo cluster. The image showed a glowing donut of light surrounding a dark central shadow, the black hole's silhouette. It was hailed as a triumph of modern science, the first visual proof of an event horizon. But hidden in the EHD's technical papers was an overlooked anomaly. The photon ring, the region where light orbits the black hole before escaping, appeared slightly asymmetrical. Some scientists claimed this was due to the angle of observation. But others noticed that the distortion mirrored predictions made by theoretical physicist Leonard Susskind decades earlier, that if black holes were entangled with counterparts in other dimensions, photon behavior would subtly shift. That same year, a team from the University of California proposed that wormholes might be indistinguishable from black holes under certain conditions. The math checked out. A wormhole that mimics a black hole from the outside could exist, its interior simply hidden from view. And if such objects already exist, we may already have found them. We just didn't know what we were looking at. Let's return for a moment to Sagittarius A star. Recent simulations using high-energy particle mapping suggest that space near the event horizon exhibits non-Euclidean lensing and unnatural warping of angles that goes beyond classical gravitational lensing. This is not light simply bending. It's light redirecting, pivoting as if guided. Could this be the visual fingerprint of a portal? To this day, no one can say for sure. The data remains inconclusive, and the interpretations vary. But the possibility is enough to haunt, enough to inspire further investigation. One more detail demands attention. In 2021, astronomers detected a rogue planet hurtling through interstellar space. It was massive, cold, and bore no sign of having ever belonged to a star system. Its trajectory, when traced backward, pointed to a region just outside the galactic core, near a known black hole. No explosion, no slingshot, no gravitational interaction could account for the velocity. Except one theory, it emerged from the other side. We've never caught something entering a black hole. But maybe, just maybe, we've caught something exiting. In 1935, amid the quiet hum of chalk on blackboards in Princeton, Albert Einstein and physicist Einstein-Rosen took a bold step. They were trying to reconcile the apparent conflict between general relativity and quantum mechanics, the two towering frameworks of modern physics. What emerged was an equation, strange, elegant, and deeply unsettling. It described a phenomenon that would later be named the Einstein-Rosen bridge. This bridge, in the language of space-time, was a shortcut, a tunnel, a wormhole. The idea was mind-bending. Imagine the universe not as a flat canvas, but as a flexible sheet. Press your finger into 2 points, bend the sheets so they touch, and create a tunnel between them. That tunnel, if such a thing could exist in nature, would be a wormhole, a gateway through space and time, linking regions that might be light years apart or even in different dimensions altogether. Einstein and Rosen didn't know if their bridge could actually exist. They were following the math. But the math didn't lie. It suggested that under very specific conditions, space-time could contain a bridge-like solution. Yet even as the concept caught fire in the theoretical world, it remained locked inside the prison of its own instability. Classical wormholes, as derived from Einstein's field equations, were inherently unstable. The tunnel would pinch off and collapse the moment any matter tried to pass through it, like trying to crawl through a tunnel made of smoke. Physicists called these solutions non-traversable wormholes. They existed in theory, but couldn't be used unless something could prop them open. That something, according to later work by Kip Thorne and Michael Morris in the late 1980s, would have to be exotic matter. Exotic matter isn't just weird, it's hypothetical. It's a substance with negative energy density and negative pressure. It defies our current understanding of physics and has never been observed in a lab. But quantum theory allows it. In fact, the Casimir effect, an experimental result involving the force between two uncharged plates in a vacuum, shows hints of negative energy fields. It's a whisper, not a scream, but it's there. Armed with this clue, Thorne and his colleagues proposed the idea of a traversable wormhole, one stabilized by exotic matter, with mouths located far apart in space-time. One mouth could be near Earth, the other, anywhere. Their motivation wasn't just academic. At the time, science fiction writer Carl Sagan had asked Thorne whether time travel might be possible through a black hole for his novel Contact. Thorne didn't have an answer, but he found one. If a wormhole could be stabilized and one of its mouths moved near the speed of light, then due to relativistic time dilation, the mouths would age differently. A traveler entering one mouth could, in theory, exit in the past. Time travel, not just across space, but across time. This was no longer just about portals. It was about causality, destiny, paradox. But nature, it seems, guards its secrets well. Even if such wormholes existed, they'd likely be hidden behind event horizons. And even if we could find one, we'd need a way to keep it open, a form of matter we don't yet know how to make. Still, theory marched on. In the 1990s and 2000s, work in string theory added new layers to the story. In these models, fundamental particles are vibrating strings, and space-time has not just 4 dimensions, but 10 or 11. These extra dimensions could, under certain conditions, fold in ways that allow wormholes to form naturally. Brain cosmology, a variation of string theory, suggested that our universe is a 3-dimensional membrane, a brain, floating in a higher dimensional bulk. If other brains exist nearby, wormholes might connect them. Suddenly, the bridge wasn't just a connection between places, it could be a bridge between universes. The theory became more robust in 2013 when physicists Juan Meldacena and Leonard Susskind proposed a controversial but compelling idea: ER equals EPR. In this bold equivalence, Einstein-Rosen, ER, bridges were proposed to be mathematically equivalent to Einstein-Podolsky-Rosen, EPR, quantum entanglement. Two particles, once entangled, remain linked across vast distances. If you manipulate one, the other responds instantaneously, regardless of space. What if this connection, this spooky action at a distance, wasn't just abstract? What if it was a wormhole? In this model, every pair of entangled particles could be connected by a microscopic wormhole. It wouldn't allow travel or communication, but it would mean that entanglement is more than coincidence. It's topology. It's geometry. It's space-time, twisted. And the implications don't stop there. In a groundbreaking paper in 2017, researchers proposed that a black hole entangled with a white hole, a theoretical object that expels matter rather than consuming it, could form a stable wormhole. The black hole would draw in matter. The white hole, on the other end, would eject it elsewhere, maybe in another time, another universe, or even another galaxy. This echoes earlier speculative models of white holes proposed by Soviet physicists in the 1960s. White holes, unlike black holes, cannot be entered from the outside, but they can be exited. No known white hole has ever been observed, but their existence is not forbidden by Einstein's equations. The key to making the bridge traversable would be the quantum entanglement between the two. If ER truly equals EPR, then every entangled pair of black and white holes might be a cosmic bridge. Now pause and consider what that means. What if every black hole is a portal? Not just a point of no return, but a threshold? The challenge remains. How would we ever detect this? Wormholes, by their nature, are hidden. If they exist, they would look like black holes to us. Dark, compact, and radiating only Hawking radiation. We would never see what goes in. We would never know what comes out. But the math offers hints. Researchers have simulated wormhole geometries and found subtle distinctions from classical black holes. In some models, light passing near a wormhole bends differently, producing lensing effects that could, in theory, be detected. Some propose that echoes in gravitational waves, faint, post-merger signals, might hint at wormhole interiors, and others believe the answers might come from entanglement itself. If wormholes are real, and if they connect entangled systems, then carefully measuring entanglement patterns in black hole evaporation might reveal the hidden bridge. So far, no smoking gun, but the theory endures. And then there are the simulations. Using quantum computers, physicists have begun running simplified models of wormholes. In 2022, a team at Google's Quantum AI lab created a rudimentary simulation of a wormhole-like system using a tiny quantum processor. It didn't create a real wormhole, but the behavior matched predictions. Entangled qubits mirrored information transfer that resembled wormhole traversal. It was just a toy model, a whisper, but it worked. The Einstein-Rosen bridge, once a theoretical curiosity, now lives in the math of quantum information, the spin of entangled particles, and the pulse of gravitational waves. In every dark region of space where light cannot escape, in every pair of entangled photons, in every burst of gamma rays, there may be a hidden link, a passage, a question, and what lies on the other side remains the most terrifying unknown of all. Let's strip away the equations, the metrics, and the models for a moment. Let's talk about fear. Because when scientists speak about black holes as portals, they're not just wrestling with mathematics. They're peering into something far more primal, a place where everything we understand about reality breaks down, where time halts, where direction loses meaning, where cause and effect blur. So what happens if these cosmic abysses are more than endpoints? What happens if they lead somewhere? One terrifying possibility is time travel. As Kip Thorne's work on traversable wormholes suggests, the different aging rates of the two ends could allow backward movement through time. It wouldn't require breaking the speed of light, only the careful manipulation of relativistic frames. Imagine this. A wormhole is created. One mouth remains stationary on Earth. The other is accelerated to near-light speed, then brought back. From the outside, only days have passed for the stationary mouth. But for the moving mouth, thanks to time dilation, years have passed. Now, the mouths are connected through a tunnel in space-time with temporal asymmetry. Entering the older mouth sends you into the past. The theory holds, but the implications are staggering. If such a structure existed, if nature allowed backward time travel, it could shatter causality. Could events in the future influence the past? Could information loop endlessly, rewriting history again and again? Would paradoxes multiply until the timeline collapses? Some physicists believe the universe has built-in safeguards. The Novikov self-consistency principle argues that any action taken by a time traveler must be part of history already, that paradoxes can occur. But others aren't so sure. In a universe with portals, predictability may be the first casualty. And what of interdimensional travel? If black holes connect to other brains, other universes, then traversing one might not just move you through space or time, but into a realm governed by entirely different laws. A place where light behaves differently, where gravity reverses, where atoms don't bind the way they do here. What would happen to a human body passing through such a rift? Would our molecules hold? Would our consciousness remain intact? Or would we emerge as something else? That's the horror of it. The unknown isn't just deep. It's layered, recursive. You don't just risk dying when entering a black hole. You risk transformation, rewriting, becoming unrecognizable, even to yourself. There's another terrifying thought. What if these portals already function as one-way valves? Some researchers have proposed that white holes, if they exist, could be ejecting material from black holes elsewhere. This means matter from other universes, other epochs, other dimensions, could already be entering our cosmos. We wouldn't necessarily recognize it. The laws governing it might be slightly skewed, enough to appear anomalous, unclassifiable, strange particles, rogue energies, unexplained objects in interstellar space. Sound familiar? In 2017, a strange object named Oumuamua passed through our solar system. It came from outside the solar system, traveling too fast to be bound by the sun's gravity. Its shape was unlike any asteroid we'd seen, elongated, possibly disc-like. It had no visible coma, no tail, yet it accelerated slightly as it exited, without any apparent source of propulsion. Avi Loeb, a Harvard astrophysicist, speculated publicly, what if it wasn't natural? What if it was a probe? The suggestion drew criticism. But Loeb's point wasn't about certainty, it was about possibility. The solar system, he argued, should be full of interstellar debris. Yet, Oumuamua was the first we'd seen, and its behavior was unusual. Suppose it didn't come from a distant star. Suppose it emerged from somewhere else. A portal, a breach. And what if it wasn't the first? Think of fast radio bursts, millisecond-long flashes of radio energy from deep space, repeating in irregular patterns. Their origins remain largely unknown. Or the galactic core flares detected in infrared that seem to pulse without clear cause. Each anomaly could be a symptom. Each could be an echo. But the scariest implication of all, if black holes are portals, they might not be empty. And they might not be passive. They might be watched. If portals exist, they could be used. And if they can be used, could they be built? The idea of artificially creating a black hole has been floated for decades. In theory, if enough energy is concentrated into a small enough region of space, a microscopic black hole could form. At CERN, the Large Hadron Collider briefly sparked such speculation. The idea wasn't that it would swallow the Earth, but that it might offer a glimpse of quantum gravity. So far, no mini black holes have appeared, but some believe a far-advanced civilization could go further. Physicist John Barrow suggested that any civilization capable of manipulating black holes would qualify as a Type 2 or even Type 3 on the Kardashev scale, a measure of technological advancement based on energy usage. Such a species wouldn't harness planetary power, but stellar or galactic power. They could use black holes as engines, information processors, or yes, gateways. If that's the case, perhaps the universe is already threaded with their passageways. Perhaps some black holes are natural, some artificial, some functional, some abandoned, and maybe, just maybe, some monitored. But to what end? Here lies the deepest terror. If black holes are portals, then our universe isn't sealed. It's porous, open, vulnerable. It means nothing we've built, no wall of gravity, no veil of distance, is truly secure. It means someone, somewhere, could reach us, or has already. The deeper we fall into the mathematics, the physics, the anomalies, the more the lines blur between the scientific and the mythical. It's no coincidence that black holes have become symbols not just of gravitational collapse, but of human obsession. Obsession with endings, with beginnings, with what lies beyond. And perhaps that's why the idea of portals, wormholes, and bridges across reality has embedded itself so firmly in our culture, not just in textbooks, but in stories. Science fiction, more than any other genre, has taken the idea of black holes as portals and breathed into it the force of narrative. From the swirling vortexes in Interstellar to the monstrous anomalies in Event Horizon, we've long imagined black holes not as static entities, but as dynamic thresholds. In fiction, they lead to other times, alien worlds, alternate realities, and sometimes to horror. But what's surprising, perhaps even disturbing, is how often fiction and theoretical physics align. Christopher Nolan's Interstellar, for instance, consulted heavily with physicist Kip Thorne, who ensured the black hole, Gargantua, reflected accurate relativistic lensing. That same film presented a fictional scenario where time dilation becomes extreme near a massive black hole, an effect that is entirely real. 1 hour near the event horizon could equal years back home. Gravity not just warping space, but time. In the story, the protagonist ultimately enters a higher dimensional construct, communicating across time through gravity. Wild. Yes, but rooted in the very ideas we've been exploring: extra dimensions, gravitational encoding, and the possibility that information isn't lost but transformed. It's a poetic truth. Science inspires fiction, and fiction dares science to reach further. And it's not just cinema. In theoretical circles, concepts like the holographic principle suggest that everything within a volume of space can be described by information encoded on its boundary, much like a hologram. If this holds true, then black holes, those ultimate boundaries, may be encoding far more than we realize. Perhaps even entire worlds. Universes within universes. It's a maddening thought. But some physicists, like Leonard Susskind and Gerard T. Hooft, argue this principle might explain how information survives black hole evaporation. It's not destroyed. It's projected, wrapped around the event horizon like a film reel, like memory on a cosmic scale. What would that make black holes? Not just bridges, but archives. Places where reality is stored, waiting to be unfolded. And perhaps that's where the terror truly lies, not in death, but in distortion. If information survives a black hole, what form does it take on the other side? Could we be simulations, echoes of entities passed through cosmic filters? Are we the output of some other civilization's black hole computation? This brings us to an eerie symmetry. Black holes, white holes, wormholes, entanglement, they all revolve around one idea: connection. Connection across time, across space, across dimensions. In a recent paper, researchers proposed that entanglement and geometry are one and the same, that space-time emerges from networks of quantum entanglement. If so, then the fabric of reality is not matter, but information, relationships, links. This would mean black holes aren't punctures in space, but nodes in a cosmic network, intersections of massive informational flow, like routers, directing the architecture of reality. And where there are routers, there can be traffic. It sounds like the stuff of speculation, but every breakthrough once did. A century ago, black holes themselves were considered absurd. Singularities? Infinities? The notion offended physicists. But now we've imaged them, tracked them, heard their collisions echo through space-time. We've begun to map their behavior. And still, they remain silent. No light escapes. No signal returns. But maybe they speak a different language. Maybe they are the punctuation marks in the universe's syntax. Full stops, commas, colons. Maybe the universe is writing a sentence we're only beginning to read. So where does this leave us? Standing on a cosmic shoreline, peering into the dark. Waves of gravity wash over us from distant cataclysms, whispering of secrets we don't yet have the ears to hear. The portal theory remains just that, a theory. No traveler has passed through. No probe has returned. But in the quiet mathematics, in the reluctant anomalies, in the light that bends where it shouldn't, we glimpse a possibility. That black holes are not tombstones. They are gates. The stars shimmer beyond the veil, their ancient lights stretched and redshifted, their messages encrypted by distance and time. Somewhere, a black hole spins silently, its event horizon rippling with forgotten data. It waits. It remembers. And maybe, just maybe, it listens. The universe doesn't scream. It whispers. And tonight, you've heard one of its whispers.